That's wonderful. I'm so happy we are. Very good. Uh, Let me attempt to find. I'm experimenting with the column major approach to tabs on the browser. Here we are. Yes, we are. This is Bill Foot, and I noticed there's a typo here. Oh my God. People will be going nuts. Can't get in.
Yes.
301 3014. Oh no. Well, we'll have to fix that like right now, or I'll forget about it.
Because
Okay.
thank God you put the correct link in an email to all of us.
Yeah. I mean, God, holy crap. Yeah. Well, that's all right. This is what it's about. We I make lots of mistakes, and uh, but as long as I can see them and correct them, we're doing pretty good. Get rid of that one. Now we're good. Okay, now let's save that. All right. Always do this so I know what I'm doing with everything. And there, voila. Ah, good. Voila. Eventually. Okay. So, Bill Foot, Larry Cosentino, thanks for joining us. It's like a
Always.
podcast now. Oh, there's the other one. Yeah, the other one is here too. So that's good. All right. And I just wanted to bring something up I put on the wall first, because that'll be the entree to what we're going to be doing next in this week. And this is a calculation of probably the most important calculation we do in the course is this, for all sorts of reasons. And it's called the highest the highest posterior density interval. You can say that fast, forwards and backwards, of course. You're cognitively enabled today. Uh, this is our interval estimation. We do not have a confidence interval. The confidence interval, I think, is the right idea for communicating results to consumers of the analysis, definitely. Uh, Give them a range and tell them your belief in how likely it is. That's all this is. And what this does, HPDI, is, and I'm going to go all the way to the bottom here. There we go. The HPDI takes the posterior curve and asks the question based on the posterior curve, uh, what is in this case, the 89% uh, range of uh, probable, uh, probable, in this case, let me get rid of this. There we go. Binomial proportional parameters, the P number that we were doing. Whatever it is, it might be the mu, it might be the sigma. Notice it goes up at a peak like this. For whatever reason, I did not, um, put in the prior. The prior is really interesting in this case. Let me see if I can go up to the prior, and let's see if I can pull this together. I'm a believer in getting under the hood, as you can see, uh, just to try. This is the probability statement itself. Between 0.33 and 0.66, uh, uh, 89% of all the possible ways that P could evolve are within this interval. Okay, that's the idea behind that. It's not the frequentist view uh, of uh, actually the frequentist view actually makes a similar statement, but we're making an absolute probability statement out of this. And again, my clients always like this. This is what they like. Uh, I built the function up here, but let's see. Yeah, here's the prior. In this one, this is out of last week's work. We're biasing uh, the grid belief, maybe based upon testimony, based upon experience, based upon certain reasons, whatever the answer is, probably all three. We think that this prior is somehow uh, related to a deviation from whatever the grid value is. Okay, that's again the idea here, and then we use the binomial. We call this an observational model. It's an unobserved number in the system. You don't actually observe binomials. This is something we come up with in our minds to reflect what we think is the reality of, in this case, 9 tosses, and 6 of them come up with water or earth, whatever the situation was. Could be reject or accept. Uh, Same idea. Um, the multiplication means both the likelihood, which is this number, and the prior must occur, and that's the posterior. You add this up, it comes up to like 99 or something. That's not a probability. So we have to ask the question, what is the contribution of this? It's all dependent upon the p grid, somewheres between 0 and 1. That's sequence by zero point zero 0.01. There's a whole bunch of those. Uh, and for each one, it contributes something to the prior. Well, that's what the next line does. It does a proportional over the sum, and it's called standardization or normalization. Our next job is to do samples. We sample um, p grid using the posteriors. Now, p grid contains the thing we're estimating. It contains the proportions, and that's that's the that's the point of it all. The absolute point of it all. Let me get in here a little bit. Go. My wife and I are conducting joint meetings here. There we go.
What does she do?
You can probably hear her.
What does she do, Bill?
Pardon me?
What does she do?
Oh, she right now she's helping to run Al-Anon meetings. That's one of the things we do, and the business of Al-Anon is fascinating in and of itself. Okay, yeah, that's fast. Let's let's see. I have to do a display here. These settings are way low. There we go. Let's put this way up so we can see what we're doing. There we go. Much better. Okay, that's much better. And is it brighter for you as well?
Mm-hmm.
Okay, good. So we take samples. We're doing a bunch of them here, 10,000, with replacement. Uh, but what we're doing is we're shaping, doing in the sampling, we're shaping p grid using this posterior probability, and then with the bespoke function that I built. Um, and by the way, Copilot gives something similar, very similar to this, which I found fascinating. Here's the function, and it follows an algorithm. We sort Monte Carlo samples, calculate an interval length, calculate interval widths, because what we're really trying to do with HPDI is we're moving this window around, making sure it's at 89, get it to 89%. And if you take the top, you see it's asymmetric. The window is asymmetric. This is not what a confidence interval does in the typical stats course. it usually assumes the shape is like Gaussian or student's T and very symmetric. That's the assumption. That is a huge assumption in the world of making decisions. In the world of making decisions, we bring something to the party: experience, data. We bring reasoning. We bring people talking around the conference table saying, "Well, what about this and what about that?" We bring all of that to bear, and that's what we're. That's actually what we're putting into this analysis that the other analysis
Bill, I
decided to
think you're
leave
frozen.
off. Uh-huh.
I think you're frozen. Now I don't hear you.
I still frozen.
Yeah, you're like I can hear you fine and I can see your mouse moving, but like your camera is not doing anything.
Wow. So you can't see that I just moved the HPDI up.
Yes, yes, I can see what's going on your screen, but your camera is not not like I don't see you moving your head, I don't see your lips moving, like none of that.
Oh no, yeah, that seems to be gone. I don't know why.
Oh,
Camera
okay.
is on. Now it's off. Now it's on. Can't tell anymore. Yeah, camera's now on, but it doesn't have the picture in the picture, right? Okay, and this is the R&D file associated with this. So if we can get through all of this together,
Yeah.
we probably have the entire inference model set up. Okay, this is basically what we do with inference in the Bayesian style, and you're done. You're basically done. Now, there's a couple of other things we like to watch and look, especially with like time series data. We want to know the interval around each data point, for example, because that changes over time. But we'll do that. That's a regression. But for this, we're done. We've done a good job. We have the parameter of interest, and there's only one in this grid approximation. So we've got it. We're done. We're happy, and we can move on. Okay. I think that's the other piece of this.
So
Um,
I'm gonna ask, kind
yep.
of a silly question, right? Um, what's the practical application to this, right? So I work in insurance. I'm looking at, I'm trying to get out of being a boiler inspector and moving up into uh process management, evaluations, and trying to evaluate, are we utilizing our field personnel in an effective, in an efficient, in a useful manner that is profitable and value added to not only my insurance company but to our clients, our
Right.
client insurance companies,
Right.
because predominantly we do reinsurance, right? So we're like, what's this like, what's the application of this to me, like?
So that's a huge question. Let's start with see if I can get back to this. No, it just doesn't want to do some things sometimes, and I need to get back to this because I can see you. There we go. There we go. And my yeah, it's gone. I don't exist anymore. So the talking head here. All right. So I mean that's a really good question.
Ignore the man behind the curtain.
Yeah, exactly. So well, all processes, inputs, the process itself, all the tasks and activities in a process, take that for example, and outputs. Uh, that's performance measurement and management from a
Mm-hmm.
data analytical point of view. And
Okay.
if we uh, have groupings of inputs, we might want to know how they relate to one another for one thing, because that will inform a decision about prioritizing inputs to the process. And there's some inputs
Mm-hmm.
that are must-have inputs, must have. And in the process, whatever the process is, you break down the process into a network, basically, of components. The next question is, what's the must-run parts of the process, and what are the things that can wait and go forward and slow down, and so on. And then when you have that, that's producing data, okay, of various types. But what this course is doing for the input and the process is it's force what we're doing with ourselves is we're going to force ourselves to make generative models with stylized facts. All right,
Okay.
not even full blown anything for that matter. And if that's the case, um, then when we do have data, we can validate those generative models. So we're doing generative work here, where we're
Gotcha. Okay.
and I think that's an important aspect of everything that we're doing, especially this week,
Do.
the second week. Now the basic model typically is some sort of regression model,
Mm-hmm.
um, but there's a lot of other models, especially engineering models or physics models of processes, where you don't have y equals mx plus b, the
Right.
simple ninth grade or eighth grade algebra line.
Right.
You have something like a times x to the alpha times y to the uh, beta minus log z. I mean that's you have some engineering model that has been tuned to that.
Right.
So it might be flow. And then the real problem of management is not just the physics; it's the human behavior side of this. So uh, what counts of teams are important to the process? What levels of skills are needed over time in the process? So you're somebody who's building a business. You conceive of it as a network of activities, a network of
Right.
inputs to the activities, and some of the activities are input to other activities with an output. And at any point, you want to touch it and say, "How are we doing?" And that's the
Okay.
data analytical problem. Okay, so
Okay.
that's where we're going with this. When we get to the end of the course, um, we're going to build something called a hierarchical model, which
Okay.
says take those nodes in your decision, because all processes have a decision point. Take a
Mm-hmm.
node, take another node, and relate them statistically. And the generative model of that is we're going to correlate their deviations from their trend, let's say. We're going to ask the question, how related are impacts from one end of the process to the other? Now, that might be a staffing process. That might be a
Okay.
scheduling process for fault detection, or whatever it is. The insurance companies use a similar methodology, and I think that'd be good to look into. Get a standard insurance actuarial text off of Amazon or Abe or AB or Thrift Books, and see how they approach is very similar to this. And they're very much into Bayesian, because the insurance company doesn't make a once and for all decision about anything. They
Yo.
they update and update and update prior insurance decisions. And the insurance decision is deductible and premium, basically. That's it. But
Well,
across a
no, I
lot of
mean,
different categories.
but they also take into, I mean, the biggest consideration that we take into is risk.
Well, it's all about risk. It's only about
Right.
risk. Yeah, yeah,
Okay. I
yeah,
mean,
exactly. Well, I mean, in engineering, I don't know. I know you have a pretty strong engineering background
yeah,
and
yeah.
practice. Well, in engineering, when we were doing engineering economics, we were looking at what were we looking at? We were looking at distributions of outcomes from a process. It might have been a process for uh, on time in full delivery of a service, for example.
Okay.
And the risk of not on time and not in full is the probability of not on time times not in full. Okay. And what are those? Both of those, each of those are conditional on a set of factors. So you build a fault tree and failure modes and effects analysis, basically, to feed those probabilities. And now you observe that probability of the full service, which is a multiplication because it's a both and they also might mix, which is the other issue. Um, it's possible, and you can do this for anything. This in operations management. So you apply this to operations management for just about anything, and you get a distribution of outcomes. Well, the insurance company wants to see that distribution of outcomes and asks the question at the 70th percentile, what happens? Because we will insure anything above the 75th percentile. That's a deductible.
Okay.
That's a deductible decision. And if we do, well, how do we add? There's a whole problem of aggregating all of those above the 75th percentile for the business and taking those numbers, aggregating them, probably with correlation, and then divide by some number to get a premium. Okay, because it's the law of large numbers and mixing it with the rest of the insurance company's portfolio. That's the other part of the problem, not just the individual insured. And those models are deeply out there, but they're all fed by this kind of analysis. That's the point. I mean, uh, the insurance industry, defies the typical stat scores, defies, because that's frequentist, that's hypothesis testing. That isn't generating the probabilities we need to figure out the deductible and to figure out the premium, whatever the situation is, and all the
Okay.
factors underneath. So you have a checklist every time, right? You develop
Yeah.
models which turn into checklists to score different activities. Then you kind of aggregate the scores and build a proposal for the insured uh, against your portfolio. And the larger the insurance company and the more diversified their portfolio, the better deal you can give the insured and keep their business.
Right.
Right. And then there's claims experience. Claims
Yes.
experience is the prior distribution. That's the claims experience.
Okay.
Yeah. And the claims experience across the board, because I'm going to, living in the Bronx, I'm going to be painted with the same paintbrush and the same paint out of the same bucket as everybody else living around me. We're
Right.
not, I act differently. So what? You're living in the Bronx, you know, and, and, that is the whole business of when we did this in 617 of the coffee problem, where we're waiting in a cafe and
Yes.
we have two modes of operation: a morning mode and an afternoon mode, and they have very different behaviors. Well, it's the same idea. It's a mode, and we need to mix the modes for the premium but we need to separately understand the probability intervals, this HPDI, to do the 75th percentile value. It's basically value at risk, is outcome at risk, performance indicator or score at risk. That's what the score. The score actually is turning the probability outcomes into a number, and that's what everybody goes on and is issued. So that's called actuarial work. Become an actuary. No, thank you. But having done a lot of the same work to help actuaries build better scoring models, yes, in the field and in the home office. So that's the insurance industry, and it's also the business of self-insurance in every company. So when I started out in banking, with all of our operational processes, we had a $250,000 deductible. This is in 1975. A 250
Wow.
quarter of $1 million deductible that we insured ourselves. And that deductible was against anything like employee defalcations, uh, uh, force majeure, acts of God, the whole nature and the whole bit, right? Things happen. One of the big ones that happened was the Chiclets factory in Astoria blew up, um, and killed a lot of people. So that was a major client of the bank.
The candy, the gum,
Yes,
chiclets.
Chiclets. Yeah, Tops chewing gum. Yeah, yeah,
Wow.
bazooka. But it was the Chiclets
Yes.
factory that got it. So, and it was foul play, absolutely foul play. I think the FBI got involved eventually, but
Wow.
yeah, and of course we had lending facilities to them, and we lost a lot of money. We lost a large client. They simply didn't exist anymore in that form, and they were there was an employee, Winifred Zucker, who got prosecuted duly, convicted of embezzlement, and there was a effectively it was an arson that did this.
Yeah.
Well, you know, she was compromised in some way, which I kind of remember, but I won't speak about. And in that compromise, the people who compromised her uh, uh, set the fire, um,
Mm,
to teach somebody a lesson,
right.
if you know what I mean. So it
Oh,
was
I
that kind
do.
of thing. But we were sitting around figuring out. I wrote the report up for it, the investigative report, and part of it was an analysis of companies like this that. Yeah, I remember I was a philosophy major doing this, but we just talked to a lot of companies that were similar to this, and what would happen if questions, and figured out what our loss would be as a bank in this situation, because Winifred Zucker was the treasurer. Okay, and we were working with the treasurer directly, of course. Their own paper was out. It was a mess. The accounts, we had liability with the accounts. Bank Secrecy Act was inside of it all. So you figure out a loss function, and that loss function is a probabilistic loss function. If you're doing it right, how likely is each level of loss as it accumulates? It's a
Okay. Yeah.
cumulative, yeah,
Right.
and that's the area under the curve. So, long story short, that's an example of something. And I got intimately involved with risk management for the rest of my life as a result of that. I mean, that's what we were doing. Called loss prevention, maybe in some places. Bags of money, you know, gone for deposits. I mean, it's like simple stuff like that, to outright arson in some cases. And when we were lending, we underwrote, like an insurance company would. We
Okay.
underwrote our client relative to our depositors, because we had to answer to the depositors and the shareholders. So you get the same flavor. Now, banks are not insurers, but everybody does underwrite. When you sign up to a job, you've underwritten something. You know, we run the biggest risk because we can't absorb the change. Uh, Corporations can because they're large organizations that diversify loss and opportunity for gain. So it's an interesting thing. I hope that helps a little bit set the
It
stage.
does.
Okay, good, good, good.
Hmm. Cool.
Because I mean the rest is kind of like why are we doing this again? And we got to keep going back to that issue. So can you see this all right? The wall.
Yes.
Okay, so
Yes.
that's where I got that, and that's why I always want to get under the hood. I mean, we take these curves and move a window inside of it to get the 89% until we get it, and it's the smallest possible window. That it's an optimization, literally, and the optimization is done not with calculus but with counting, and that's why I keep saying that the course is really about counting. I make the promise to a lot of people you need to know really well counting up through fifth and sixth grade, but from an adult point of view. A lot of people don't. They just know, multiple choice answers. And ninth grade algebra, because you really don't need more than understand polynomials, let's say. That's about it. Everything else is pure counting. And I like that because to me, if I can't get it down to counting, I can't do this. I can't get these instructions to a computer. All the computer does is count. They do not do calculus. They do counts that look like calculus. So I thought this was a very good example of an optimization, minimize the intervals such that it's a constrained optimization, such that two things occur. The highest posterior probability is in the interval, and and it's the smallest interval, and that's what we get with this. So that's kind of interesting with that algorithm, and that's what's inside of counting on Bayes. Uh, Solving problems. This thing right here, where you see this box, that's the entire Bayesian setup right there. I call it a box of Bayes or a Bayes box. All right, and now we go with our practice. This is this. What week is this? That's just week one. Yeah, heavy duty front loaded week. That's what we like to do. Front load, major, minor, conclusion. Play with it, but yeah, this is called modus tollens. Yeah, I've actually written an extensive paper on all this, which I will share. But this is week two now. We're into waffles, divorce, milk, uh, and I like this because it's takes us out of the context of what your question was. What do I do with this in my business? And now the reflection is how can I use this weirdo example? It's weird because it's not my business. It's not how it's not insurance. It's not running a risk management operation in a financial firm. It's not whatever it is my business. Running an educational institution. Um, the very operation of analogizing this to your business will give you more insight than if I gave you your business example. Much more insight. That's just the way our neuroscience works and the way our spirit works. Dag damn it. Okay, the directed uh, acyclic, meaning they don't run in cycles, they don't run in circles. There's no feedback actually. Graphs, some way of picturing and analyzing causality is what's inside of this. And I have something else on this too, but let me just pull this up for a moment. So these are warm-ups. You already have the answers to most of these. The point is to use those answers, go through them, and make them your own. Here is the first big generative model. I is an index here, students, and J is the year. So instead of a student, you could say a client. I mean, same idea, and the year. And you're simulating something about the client uh, uh, across time. So it's a space-time situation. It's no different than physics. Space and time is what we talk about there. But the spaces we talk about are usually decision spaces, and the timing is, say, a fiscal calendar, right? That's how we would look at it. Or the time between now and the exercise of an option in a contract, which is another thing. To think of your management problem of allocating resources as a portfolio of options in a contract, where the exercise price is how much you have to pay to exercise the option, and the premium is the upfront investment to get you there, to get you to that point, to have that right, to buy something or sell something, basically, to trigger an activity, or to let it stay the way it is, business as usual. And that's a portfolio of options point of view. And that's easy to simulate. In this one, we have height, okay, and years, and we have the age of students. Okay. Hello.
Hello, it's Larry.
Yes.
Hey, I lost power, but I got it back.
Okay, let me get you back in. There you go.
Thanks.
You're welcome. You're back in business?
Now I'm back in business.
I'm not back in business. I don't know what's the matter with me here. There we go. Lots of things are the matter with me, but let's see what speaker view maybe. No, Bill Foot is still playing. And I think didn't matter. And one more thing I'm going to check before we go. The video is messed up. There we go. I'm back. Nope, not back. My video. Nope, doesn't want to do it. That means I have to get into Lenovo to solve the problem. So I'll put up my. That's a little picture of
Arizona, Nevada.
No, west of Barcelona is a range
Spain.
called the Montserrat range. Yeah.
Okay.
And that's kind of there. Little 6x6 gouache painting.
Nice.
I like it. Thanks. Yeah. Rather look at that than my face these days. Okay, so we were looking at this. Piece up here. I gotta get rid of all these things, obviously. Oops. Trying to figure out something that was very difficult yesterday. Unnaturally difficult. Okay, let's get rid of this. And here's the skill builders that we need to see. Good. And again, what this does, this block down here is that generative model. it basically says something that's indexed by uh, uh, actor I, agent I, um, project member I, and J, which is a time subscript, okay, is normally distributed. I need to fix that someday with a mean and standard deviation. The mean is modeled as something that doesn't depend on Y, the year. The year is J, and that something might be just a regular trend. So this is if the mean is the mean price, this means this is a non-price effect, as an example. Beta is the impact parameter, and we're using a technique which is called centering. We're centering years around the mean year. Now, this is a statistical trick, but it's also a way to get inside of alpha beta minus beta times y bar, the average year, okay, the mean year, and that makes things constant. So that isolates, if you will, isolates beta and the impact exactly on the year, but also plows into the analysis something about years that's relatively constant or a trend or what we can expect. Okay, that's the idea there. And alpha and beta are in turn sampled, uh, normal 100 and sigma 10. You got to play with this one, given the data. And we're using just stylized numbers here. And the beta is 0 or 10. Sigma is given the exponential distribution, which is always going to be positive. And you got to play with this one as well. What is this parameter lambda? What does 1 mean? Well, try 2 and see what happens. Try 0.5 and see what happens. And this is how we play with it. I find that is a better thing to do than to do a rather complex algebraic analysis of the exponential function, which is an interesting exercise in analytical acrobatics in your mind on a piece of paper. But it's better to play with it. Okay, that's what I'm looking at here. And so here we're going to have 50 observations. You have 50 people in your team. A is going to be normally distributed, and we're going to say A is going to range between is going to have a mean of 10 of 100 and a standard deviation of 10, and it's just going to be a bell curve. Now, in this chapter, we also discuss what the bell curve means. So I'm assuming you've had some idea. It describes any kind of event that converges on a central location. That's all.
Yes.
Things far away from the central location are less likely. Things close to the central location are more likely. That's all it says. And then there's math to it, but that's all it says. And I like that because that's how I'm going to communicate with my team. Here's our performance goal, and we deviate from it. What's most likely to be that deviation? A small deviation from what our expected performance as a team is, how many tasks we can perform in a unit of time or whatever it is, as opposed to things out in the tails. And we will register what those things are. We'll have a discussion, a substantive discussion about our work. And that's a great way to have a discussion, is to talk about it that way. There are in insurance, however, because you did raise the insurance issue, there are in insurance tails of a distribution. And those tails are not, they don't converge to a mean. You can do a mean. You got 10 players on a team. They're all 5'5", and then you have a 7'3" player. Okay, outlier. Well, no, it's just a 7'3" player. I don't like people called outliers. That's just nonsense to me. is part of the information set. And we're very happy to have that person on the team, by the way. especially for somebody like me who's 5'10". I need to look up to somebody. But you take the average, it's meaningless. You take the standard deviation, it's even more meaningless.
Right.
The statistics just don't seem to matter. Okay. So that's a different type of distribution. It's called an extreme value distribution. It's something that we should be doing a lot more of in management, because we pretty well have figured out how to do things when things go well. All right. That's
Yes.
the center of a distribution. It's the tails of the distribution that, it's the 80-20 rule. Well, the 80-20 rule is one of those extreme value distributions. Okay, so there we go. The 80-20 rule with that can be estimated. People with an awful lot of money, are a very small percentage, is an example of that. And we see that all the time. That's how we do inequality studies. But there's a lot of inequality studies. Some customers, because of where clients, where they are more apt to lose assets. Well, because maybe they work in a war zone, like Médecins Sans Frontières, the Doctors Without Borders people, right?
Right.
How do you insure them? They are insured by Lloyd's, which is not a limited liability insurer. You join a Lloyd's group, it's full liability, positive and negative.
Interesting.
Yeah, very interesting. And they've been doing it for a very long time, so they have a very good idea of how to do it. So here's our generative model. We're generating values for A and B, and S, the sigma. We can do plots and summaries and all of that. We have, I don't know why that didn't work, simulated in 3 years. Now, this simulation uses a matrix, and it does 2 for loops. The first for loop, the outside loop, is on, in this case, the numbers, the students, the 50 students, 1 to n. And the inside loop, for each n, we go 3 years. So each student gets 3 values. That's what the J loop does. And this is how we code it in. It looks similar to Python. You should try this in Python. I would just put it in Copilot and say, translate this to Python, please. Because I'm done learning yet another language.
You really don't like Python.
No, I don't. I don't like the style of it. I don't like there's a bunch of stuff I don't like with it. I like it. I like it as much as I like C or C++. I don't like C++. I like C. Right.
Okay.
So, okay. And I probably want to go back to Fortran, before I expire, just because it's so simple.
Yeah.
But don't ask me to go to assembler. That's too simple and very hard. But here we have a matrix. Okay, it's going to be a matrix of I rows and J columns. And we'll have 50 rows and 3 columns, basically. And our norm, and here we go, we're simulating all of this. Now, what is this simulation? It is this top line here. So we simulate this, we simulate this, we simulate this, dump it into this, dump that into this, and that's the final simulation. So this is a simulation order. And you asked the question last time, can you put it in opposite order? Yes, you can, because effectively you are doing it that way. But what we're doing here is we put the high level first. It's a notational standard that we use, and then say, oh, where does mu come from? Well, mu is here. Well, where does alpha come from? It's here. And beta, where does that come from? It's here. And sigma. Now, these numbers are are simply the years, and it's just 1, 2, and 3 in this case. So very, very simple. And what we do is we plot it. And this is I'm using straight out of McElreath. We're not doing ggplot2. We can, but I think with plotting we just take whatever's the easiest thing at this point, and this might be easier than doing ggplot2, because you can do something like this. You can do all of these lines, and there's a way to do this in ggplot2 as well. Doing this in Python, first time I tried it, it was a little acrobatic, but I think they vectorized it and so on. And you can also vectorize this as well. You can vectorize this using the apply functions in R. But look, these are sticks all over the place, and the thing they're asking is, okay, you're 1 year in, 1.5 years in, 2 years in, 2.5, 3. Okay, so as you grow older, your height in centimeters, well, are you shrinking? So there's a common sense clause comes in here. Oh no, that's nonsensical. That prior is nonsensical. This one's okay. It goes up and up and up, and this top one's okay. And like there's a kink, and then you grow a little bit faster. All right, from 2 to 3. But these negative ones don't make any sense. All right.
Right.
Right. So I mean, unless there's traumatic things happening to the body, which hopefully isn't happening. So we go through that and we play with that. So what do we do now? We try something to make it more reasonable, and this is the result of more reasonable down here. We still get some bad sticks. Hopefully not as many. This one here, whoop, we drop off. And slightly shrinking here, spinal compression. This is not nice. Do the same thing, and now we're saying, what do we put in with B to make it positive? Okay. Well, what we can do. Well, that's the question here to make it happen. Simulate and plot. And what do they plots indicate? Well, we're still in trouble. And then we rewrite the model as what? And here we get a new model. So all of this was trying to get to the idea of using the log normal distribution. And this is another one to play with. So we just do this. And we're using rethinking. And we pop it in here. No, we can't talk. No, we're not talking. We have some folks outside that want to give us some spiritual literature, and we're not. I usually do talk with them, and I have I set, my goal is to set them spinning, and I do that. Okay, let's go back to here, and I just want to bring up the course, and here's the R builder. Call these skill builders. We just need one. Let's see if I can get it download here. And you put your names up there. So the warm up, wind up in the pitch. Okay, this is all what we just did. Lots of summaries. And basically, it's plotting this. and whatever numbers those are. I think we finally fool around and find it's 0 and 1 will work fine. How did we know that? Practice. And reading McElreath. But simply practice. What does a 0 do? And what does a 1 do? Similar to mean and standard deviation, but from a log point of view. And let's see what we come up with here. Yeah, mostly right. See what that did. We still have a couple of oddballs here. Okay, but this prior will tend to work. Okay. What am I saying prior? That's B in this height is normally distributed with mu and sigma. Mu is this, in this particular case, weight. And same as the other one, we played around with years. Weight is a very similar thing. And we want the impact of weight always to be positive. If the weight drops, we want the impact to be a positive on the drop, therefore a negative. See, I mean, that does work. Sigma can also use the uniform distribution. We typically use the exponent. And we're using data from Howell. Well, what is Howell data? Let's see if we can do this here. And we're looking at ages greater than or equal to 18 in this problem. And that's how we do the indexing, D age, and so on. But we need to see what D looks like with Howell. Let me put this down like this. Okay, Howell 1. Who is Howell? Okay, let's look over here. Demographic data from the Kyungsan people collected by Nancy Howell. So this is the Kalahari Desert. Wonderful people. They survived. The rest of us are killing each other off, but they seem to survive somehow. Good stuff. Oh, tooth growth. No thanks. And what's Howell 2? Okay, I guess it's similar. Okay, now what does Howell look like? And, well, that doesn't make any sense. That's because I did not do this. There we go. Height, weight, age, and male and female. So it's roughly split between the two genders. And we have a minimum and maximum. So this is the first line of exploratory data defense that we have. We have ages going from 0. What's a 0 age mean? Just born, maybe, to 88 years old. Okay, that's pretty good. But third quarter is 43. There's a big distance between 43 and 88, isn't there? 0 and 12, okay, but 43 and 88 is a big one. So you can see this is a highly skewed distribution. And this is almost as skewed, the weight, 62, probably kilograms, right? 53, these I believe are centimeters. Okay, the CGS system, or the MKS system. And then we can run all of this. Let's see what happens. And this is what happens. It doesn't work. See, so you need to try it again. This time it worked. So I'm glad that happened because somebody's going, what do you mean it doesn't work? What do we do now? Just run it again. All right. And the reason, as McElreath explains, and I wrote a little something on this as well. is that the optimization routine is optimizing a very irregular surface, trying to find the maximum likelihood, posterior likelihood possible in a very, very irregular surface. So it has a starting value, and the starting value just doesn't work. you start in the valley, and you stay in the valley, and you want to get out of the valley, and it won't let you. Okay, that's the idea here. So just try a different starting value, and these are random starting values in the way this works.
So what's with that line that starts at 70 and looks like it goes up towards 110? Yeah, that line there.
Yeah, that's somebody who grows really fast in 3 years. I guess the hormones really kicked in. Again, your statistical model may be nonsense. All right, I think that's nonsense. Just like there's a couple of negative ones here, right?
Yes, I
You're going to.
they're just harder to see.
Yeah, they're very hard to see. But here's one. It comes down, and bounds back up. And I don't know.
Yeah, like
I mean, that this is statistics. This isn't real life, thank goodness. And this is just
right.
a generative model. But if we looked at the height here, it's all positive, right? And the data is weight is all positive, and everything's in the correct direction, and the proportions of male that probably by design. I think Nancy Howell got 50%, roughly 50% male, 50% female. But the males or females in the model, how do they relate to height and weight and age? That's the issue. And this is demographic. You have customers, for example. You have customer demographics, right? So you might say, here's the customer profitability. We get this much profit from this customer. We get this much benefit from this customer. We might ask, how big are they? Weight. We might ask, how long have they been with us? We might ask, what industry or subsector do they come from? Same model, just different. I mean, if I told you this was customers and not height, weight, age, and male, your client list, you go, oh yeah, I get that. That's what I'm saying about analogizing. What
Right.
people are, and that tends to work, I think. And we got an answer down here. A is 114. There's an impact. There's a sigma. We've also estimated sigma, which is implicitly estimated in ordinary least squares, the usual regression model. And in fact, if you ran ordinary least squares on this, you probably get something very, very similar. Gosh, can I do that? See if I can remember how to do that. LM formula. Height tilde, what is it? Weight D. Call this OLS fit. Yeah, I'm having a fit, all right. And that seemed to work. And then do a summary of the OLS fit. We'll probably get something similar. No, we don't. We get 114. They get 75. We get 0.89. We get 1.76. Oh, great t-values, wonderful. By the way, our t-values would be really good too, but we don't believe in t-values. That score, take this number and divide it by that. No, we're looking at the HPDI. which is between 111 and 117. That's pretty tight, if you ask me. Right? And 82 and 96, pretty tight. And you can plot this if you want. We can run all sorts of plots and make pretty pictures, just like we did with globe tossing and the HPDI intervals. But that's what these are. These are not confidence intervals. These are credibility intervals, probability intervals, highest posterior probability intervals. Very, very different. And we're going to run our inference based upon this. Why are they different from OLS? I think it's because we're also estimating sigma. There's three parameters in this model, two mean parameters and one risk parameter. We have a risk parameter here, Larry. Yes. The guy who does risk management. There we go. We have to kind of get it out of here somewhere. Residual standard error is 9.3 on degrees of freedom. We don't care anymore. What is it? Yeah, ours is 5.01, and it has a standard error, a standard deviation, a width. That sigma has a width between 4.74 and 5.34. Okay. So we're already way ahead of the curve here than these guys, and I don't even know what this means anymore. It says the it's called stargazing. Lots of asterisks means little stars. Lots of asterisks means, oh, it's too good to fail or something like that. Anyways, look, totally different numbers. All right, so I'm sure there are other reasons for this that we can get this. And then you have, this course is designed to bury once and forever the use of R squared, but we won't go into that yet. See, I have an opinion about these things.
Well, I'm glad I did Alan's class first.
Yeah. Oh my God. He didn't do Bayesian in your class, did he?
No.
Okay,
but we focused a lot on R squared.
Yeah. Okay. So you got it. Get it out of your system is all I'm saying. So what if we did other ages, pre-voting ages? These people, I mean, they run it's hard to describe a share and share alike philosophy. That's how they survive. It's the rule of Saint Benedict. It's a generosity rule, not a democracy, not a totalitarianism, not a they have elders to guide. A lot of so-called free choice, and a lot of growth and transcendence within their context. These people are relatively happy. I mean, they're some of the happiest people on the planet, apparently. Don't mess with them. Leave them alone. Very interesting. But if we rerun the model in the text, what was the model in the text? I don't even remember what the model in the text is. No, that's why I gave you all the models in the text in this rethinking file. And so I just have to go up there and get it. Oh, it didn't come up. Well, that doesn't make any sense. Huh. All right, let me, oh, I did this. Multiple files. Now I know what that is.
You got to unzip it.
Yeah. No, it allows me to, this must be in download somewhere. God knows when, from 3 years ago. Okay, so what we're going to do is we're going to look up Howl. And this is where all the code was from the book. And now we're going to reload the model. Plus, we have all of this other stuff we can do, which we will. But I wanted to, here's Howl again. Extract samples. And I'm going to get to it eventually. And here's the model with X bar. Here's another model taking it out of the log normal. Exponentiate a log, then you get something else. And you go through all of these things. I just want to see that we're doing this the right way. Okay, let's work on this code here. And go through some of this stuff. I think this is useful if it works. Some of this doesn't always work in R. Yeah, let's go back up here. Sorry about this. Okay. So we have this X bar model. That didn't work. We're taking the mean weight and we're doing this centered thing. And we're going to compare the two models. Oh, come on. I think I don't know about what my fingers aren't doing the right things. There you go. There we go. Okay. And so we're calling this D2 right now. I guess we'll call it D3. And I'll change it down here to D3. We're just reusing a model. I'm going to say not X bar. Let's call it W bar for weight. I think we can do that. That means we have to change it down here. Okay, now I think I can read this. Pre-voting age. And what I like about the Précis is it gives you these line by line histograms. You can turn that off. You just read the Précis instructions and you can turn that off. But you got a mean, weight, age, male. I like that. Okay, you can see what the distribution of weight is. The distribution, you see pretty much barbell for the males. Female, male, and no male. Age is exponentially distributed. Okay, in this, and that makes sense. In a population, there's hopefully more, but we're just different now. As we're getting older, we're still around. I don't know why we're sticking around, but you know, theirs is definitely this and weight. And we're trying to relate each one. We're trying to relate this and this, age and weight to height. That's what we're trying to do. So we just did that, and now let's run this model. And we ran the same problem. There we go, finally ran. Yikes. Took 2 tries there to run this model. And we want to name this the price of M4.3. And there we go. It does change things. It changes B. It changes the mean. They're still very nicely, even more tight. Look at how tight that is. That's extremely tight now compared to our other model, which is Précis 4.3b. We're going to compare this with okay. So what the question is, what does centering do? Notice the risk parameter that we would call sigma is higher. Okay, that's one. The centering, the deviation of weight from its mean, has a higher impact value on a 2 as opposed to 0.89. And a 2 can be thought of here as almost a elasticity. Like a beta in finance. You're familiar with that, Larry?
Yes.
Yeah. 1 is, it's really an elasticity. It's a percentage change of an asset's return relative to a percentage change in the market's relative return, relative to the market's return. And if it's greater than 1, it's risky. If it's less than 1, it's less risky than the market. If it's equal to 1, it's as risky as the market. That's the financial interpretation of it, of a beta.
Right.
Because the beta is a covariance divided by variance, basically. And if that's the case, those are, to me, nice risk numbers. Covariance and variance are very good risk numbers to play with statistically. And that's what the sigma is trying to say. And that's what the B is trying to say. And that A is smaller. But it's also, look, a lot tighter. So centering tightens up the regression results, tightens them up in the HPDI sense. This interval is going to be smaller. This one here is, but this one widens. Sigma widens. And we might think of why. What is sigma here? So again, if height is customer profitability, and weight is the size of the customer organizationally, got a lot of people, or they're spread over the world. There's some weight gravity factor in there. And age is how much experience do we have with them? All of that. But the weight here, doesn't matter as much as it does up here in the centered sense. We look at deviations, and deviations are also useful because, again, we often in management think of risk, how deviations from a trend, right? And we also will think of things like mean reversion. How fast does a trend revert to its mean? And the impact of that reversion on, in this case, height, or if it were customer profitability. See, those are good questions, right? Very good questions to ask. So just getting to the interpretation here is probably the most important thing. Once we get all this mechanics done, it's that. And we can parabolic model. There we go. What if we changed it to this one? Let's just try this, okay? You game?
Yeah. I got about 15 more minutes.
Okay, good. We'll do this because I think this will be very helpful. Okay. Well, this M4.3C. And do a co-op on it. Now remember, we had to do it twice because of the nature of the optimization routine going on underneath. And we're going to put in this mu. We're going to need a log. We're going to call it, okay, W bar. And I'm just going to, because I don't want to type anything in. I screwed that up. Okay, good. I don't want to lose any of that. Let's put it back down here. So same height model. Now we have mu there, so we need log W bar is assigned from log W bar. We'll find this will work better than having it computed. And I think we got almost everything there. So let's put the rest of this in here. Make sure there's commas here, because that's a list, not a dot, a comma. I have to apologize for all these goofy things going on. I have an eye condition in my left eye, which I periodically have to close the eye, or I can't.
When are you having that surgery done?
Next Wednesday.
This coming Wednesday, or
yeah, this coming Wednesday. Yeah, and I won't be able to see out of this eye for quite a while, apparently.
So we're not meeting on the 26th, or is it going to?
No,
just
we'll still meet on the 26th.
Okay.
One eye, it's going to have to do some extra work, but you know, the problem with the left eye is it screws up my line by line reading because it's trying to mesh together. My brain's trying to shut it down. Actually, we have M4.3C WAP thing. Okay, log weight. See if this. Let's just see if this works. I'm going to set A to 114 now, because look, this is how I use extra knowledge, right? See, we got a mean of 114 and a standard deviation of 1.88. Okay, 114. 2. I don't know if this is going to work. We'll see. Okay, I mean, please, you know, we'll just see. Maybe this is 5. I don't know. Let me see what happens here.
Okay.
unexpected comma somewhere
in front of the data. No, 2 lines down after that parentheses.
Yeah.
No. At the beginning of the line. So you,
Yeah, it looks like this, and this worked
oh yeah. Huh.
because there's no A list. There we go. There we go. Now match up, will you? Okay, now it's all matched up.
There you
We don't
go.
need that one. How about that? Okay. Well, I got to be able to type it in properly. Use my right eye. There we go. Oh, good. Okay, now that would do it. And it ran. And now look what the logs do. Okay, so if we modify, if we play around with the data, we can come up with any story we want, pretty much, right? That's the way I look at this. Now, there's one more thing apparently we can do is make B, raise it to, let's see, we have just a EXP, raise that to 50. It's huge. What if we take log of 50? Yeah, we're right back to business. Now, this was a log transformation here. So because these are smaller scores, I mean, if you look at what this is, of course, I have to make this, what is it, D3. If you look at what these are, they end up being like scores, right? Between 0 and, positive and negative, depending upon whether they're above or below the log of Y bar. Now, again, in the insurance industry, you use scoring a lot. That's what the log does. The log is really more of a scoring approach as opposed to exponent, which is more of the growth, the actual growth and the actual level approach. Very, very different types of measures. So then the question becomes, what is B relative to weight? And the answer to that is log B, or log 50 in this case, is 3.91, would be the equivalent B value for using raw weight again. And again, we did see that already with this one. Yeah, it's in the same league. It's not the same, but it's in the same league as using just weight and bar. Okay, so we can play with this until the proverbial bovines come home. You can take this and make a parabolic curve. Partly,
Nice question.
sure.
Why did you do the precise M4.3 and not M4.3C?
We can compare them.
Oh, okay. Okay.
That's just a comparison. So we got a 50 here, and I was trying to say log 50 gives us something in the range of what we had here. They're not
Gotcha.
the same because there's a little bit of apples and oranges going on, but the scoring method produces different results, as you can see. Okay, that's That's all the thing I was trying to get at, the scoring.
Gotcha.
And it's also because B is log normally distributed. Just that's where we're sampling it from in order to get positive values. You can use other distributions to get just positive values. We think that B has to be positive. Okay, the larger, the more. All right. Now, if you're talking about customer profitability, that might not be the case, by the way, where weight is size or complexity of the organization or complexity of the coverage. I mean, you come up with a complexity number for the coverage based upon the number of interrelated sectors under the general cover and the special covers. You might use all those as nodes and count up the nodes and say, we got a lot of connections here. Okay, one to the other, called complexity. And complexity and profitability, the height analog, might be negatively related. I don't know. Depends, upon the data set and the business questions being asked. But I think we've come a little ways here, shape and all of that. The next one starts to look at kilocalories, the size of the neocortex, and M, mass, how big you are. And these are cases. And this is milk mass and the neocortex. Again, same sets of ideas. You have let's see, what do I have here? You have a prior, got all sorts of things we could use. In this one, we have a model of M and N influencing K. Now that's much more realistic. This is where we're getting into the DAG idea, where we have two factors influencing a ultimate dependent variable called K, and doing the risk analysis. And there's a mu and a standard deviation. But we also have M influencing N. So your two factors are related to one another. This kind of modeling is extremely interesting now. Now, there's a mediation going on. M, the amount of milk, and the neocortex, that is fed into M here, and we not milk is by itself in two places, but N gets fed into here with milk as a determining factor. These are all linear models, and we can write all of this down and make it all happen. But again, I gave you the solution to this. I just want to portray that solution, look at it in the last 5 minutes, I guess, that you have. And hopefully, let me see, where did I put that? I put that in one of the weekly discussions up here. And the wall. I have Moodle access. Good. Here are the solutions. What was the number on that? 5H3, M5H3. There we go. So in this one, again, we take rethinking. We have data on milk. And primates, data, table 2 of Hein and Milligan, evolutionary anthropology. Now, I find more insight for economics out of evolutionary anthropology than I do out of economics. The same for management. I get it out of places like this because, again, it forces me to think differently about a lot of things. And then analogize, which is a skill and a capacity. More skill, more capacity in that. So it's like milk, I guess. But primate milk data, let's just look at it quickly. And we're going to standardize it because we saw standardization tightens up the HPDI intervals. And we got percent protein, mass, neocortical, percent fat, weight. Is it old world or new world monkeys? All sorts of species. No bonobos, though. I don't believe. Okay. And other. Okay, good. 23 species. And makes it interesting. Okay. So we wouldn't have that. We would if we're Nestle and you want to look at loss operations, you're going to look at milk production. They make milk, and we have one species, but we have people living in different areas. Would be the analog of that. Okay. And losses in that category would be interesting. So we have D. We standardize it. That means we center it and divide it by its standard deviation. So now these are called Z-scores. And you may have discussed that at some point. And we're only looking at complete cases. No things that are oddball here. There we go. Things with missing values and so on. We just want complete cases. And we're going to run this model where milk and neocortex percent feed K or a weight category. It has its own model with its own pieces here. But it's mediated, N is mediated by how much milk, which is science too. Science is inside of this. And we have priors all over the place. And we're going to run the trace C next. And there we go. So we just did a hierarchical model with statistical causality in it. This model is got to be your primordial model whenever you do anything with multiple regression, anytime. Okay, this is like a simultaneous equation, multiple regression. It's actually hierarchical. There are different levels. There's a level for the grand result, which is K, but also for an intermediate result, thus the word mediation here, which has a mean and its own standard deviation. So we have something here called heteroscedasticity in this model. We do not. You can fix a ordinary least squares model with that, but the typical thing is, oh well, the residuals all have the same standard deviation. We do not have to live with that highly constraining condition or assumption. We just broke it right here. We broke it up into two pieces. There's this regression feeding this regression. Larry, if you look up two-stage least squares, which is a problem somewhere, okay, you'll find something like this. But this is tighter than that. And look at how tight. Go ahead.
Yeah.
See, so these AKANs are crossing zero. Okay, so they range from negative to positive. not very tight. And if you're doing t-stats, you can see that here, but we don't do that. This is a good one. I like that. This is a good one. This is a good one. These are what matter. These should be close to zero. These should be close to zero. The reason they should be close to zero is that we're running z-scores. By the way, z-scores add up to zero. They're mean zero, standard deviation 1 usually. All right. Standard deviation 1. Well, you combine these together, you get a standard deviation of 1. Weighted average of these two would be close to 1. And they're tight. Yeah, this is less tight. Okay. But we have that, and yes, why not?
So,
And let's ask another
thank
question.
you, Bill.
You all set? Good.
Yep,
You're
I'm
very
good.
welcome. Okay, good. And thanks for joining me and all
Always.
of us. And, you take care. All right.
You do the same.
Thanks. We'll do. Bye.
Bye.
Let me continue with this discussion just for a little bit. 2 skill builders. And we have weight-centered models and pre-voting ages and playing with that. The milk piece is, I think this model, the mediation model, is an important development in our model building right here, right now. And with this, what I want to do is do this sequence of activities in order to build something that I think is helpful for us to see exactly. Okay, let's go back to this. Here's the code in 512. And this is the divorce piece here, and marriage and waffle houses, waffles and divorce. But again, it's going to follow much the same idea, where we're going to do some DAGs, and we'll do that in a separate segment. But here we have a multiple regression again. And looking at dependencies and attempting to manage those. So entropy will be the next big thing. That was a favorite topic of mine. But let's get back to what I think is a very strong template model for us. And we're just looking at this 0.74 for milk, levels of milk, just 2 levels of milk. And we're going to do some simulations based upon just those 2 levels. And we create a little data frame with it. We dump it inside of one of a very useful function inside of rethinking is called sim. Where we're saying that simdat, we're applying this to our model, and we're running it across. We want the other variables. So m is determined, and then we're going to figure out n and k. More m gives you more neocortex. More m and more k. More m and n give you more weight. I mean, that's kind of what we're looking at here. But this simulator will calculate using model parameters that we've just estimated, these parameters right here, holding m constant at 2 levels. So we have this already. And now here's a simulation. And now here's the diff. Now, just let's look at S for a second. First of all, let's do the head of S. It does 1,000 simulations, drawing from the model. Get back to the top here just so you can see. And it has K is being simulated. You can guess that this must be N is simulated, because that's what we asked for. And 1 and 2 refer to 0.75 and 1.15. So now that we got our legs around this, I just did a head. Gee whiz. 2 elements in that list. I want to just do structure on the bottom to see what the structure is. There we go. It's a list of 2 items, 1,000 each, 2 columns, 1 and 2, each for our 2 simulated numbers. Now we can put a third one in there. Yeah, means of log d mass and mass. Good. We can put a third one in there, getting somewhere in the middle, and see what that looks like. But that's not necessary. We do the diff, where we're taking out of this list K2, this piece right here where my cursor is, and minus all of these, all that the diff. And we can do quantiles, but why can't we do HAPI? But let's just do quantiles for the moment. And we get a 5%, a 50% quantile, and a 94% quantile. That's what we've asked for. So we kind of do a little study of what this is. This is the median. This is close to the max. This is close to the min. Okay, so actually, let's do this. Keeping with our 89% ranges. There we go. That's a little more exact, but it's close on. So it's almost 2. Okay, we get to almost 2. And this is the difference between K and N. Okay, in terms of those 2 standardized numbers. And remember, these are z-scores. This is a difference of z-scores, difference of scores. And we use scores in a lot of places. And again, when I was working in the healthcare insurance industry, that's all we use is scores. And there's a consultancy called Merriman that came up with incredible models, but all based on scoring, which is endemic to that business, but also very useful in project management, for example, scoring. Okay? And scores are based upon actual data to the extent possible, not just Likert scores of unlikely to very likely, for example. So we just did that, and we can also do something like this, where we go from -3 to 3. Now that's 3 deviations versus less than the mean, and 3 deviations greater to the mean. Deviations, standard deviations, right? Z-scores. We're going to do 30 here with that sequence. Put that into the SIMDAT data frame. Introduce that SIMDAT data frame and apply it against the model, all of its things, and we still want N and K. Okay. And what do we get now? And now we can process this. and get lots of quantiles. Yes, we can. Look at all the quantiles we're going to be able to produce. And this ought to be a weird one. There we go. And now we have pretty much the same thing. You know, even widening the z-scores from 0.75 to 1.15 to minus, still coming up with the same differences, showing the stability of our, among other things, many other things, the stability of what we were trying to do. Okay, so that was great fun. And we just did all of that. Why did? So get into that. And 5H4 will save for a separate reading because I want to talk a little bit more about directed acyclic graphs. And this is a great place to stop right here. So let's do that. And thanks to Larry for dropping in and hearing all about my crazy life, but not so crazy, just normal. Here in the Bronx, broadcasting live today and Saturday, July 19th. And hope you all have a great weekend. And let's continue the level of education and the level of fun. Let's keep both of those very high. Take care.